Okay, so to refresh your memory, please start doing this example that right now you see on the display. After 1 or 2 minutes, I will come back and solve this problem for you, and then we continue. Okay, so now I think everyone is here. So let us start solving the problem. Yes, so so you know that if you want to write all the subsets, first of all, what is the cardinality of this set? We have one element here. The second element is this one, and this one as a whole is one element. So the cardinality of A is just 3. And if you remember, the number of subsets of this set is 2 to power the cardinality of A, which is 2 to power 3, which is 8. So that's a good thing to remember, that you are not going to ignore some of them. So you have to write 8 of them. Okay, and then you know that we had a theorem before that empty set is the subset of every set. Every set is also a subset of itself. So in some sense, the empty set is the smallest in quotation, subset of a set, and the set itself is the biggest, again, biggest is in quotation, the subset of itself. Okay, so usually if you want to keep, of course, order is not important, but it is better to keep the order to be organized. So I would write, the first set that I would write is the empty set. Either you write this with this symbol or you write this in this form, nothing else. Then I will consider one element subsets. Yes, so this is very important to have the correct number of curly brackets around. Okay, so that's very important. And so that's the only probably thing important. If you don't do that, then you will lose that the point for that one. So I will open a curly bracket and I put the first element inside. So I will take this one and put it here. So this becomes the first one element subset. And then for the next one, again, I open a curly bracket, a pair of curly brackets, and I will take the second one and put them inside here. Yes, so this becomes this. This is the third one, yes? And the next one, I open again a pair of curly brackets. I will take this one and put it here. Okay, so this becomes curly, I'm sorry, it becomes curly 1, curly brackets 1, 1, something like this. So I have only 3 one-element subset of this set. And then I consider 2-element subsets. So let me write it in a different row. So I will put a pair of curly brackets, but I will choose 2 of them. For example, this one, and transfer them here, both of them, yes? So this becomes 1 and curly 1. For the next one, again, I open a pair of curly brackets. I choose another pair. So for example, this one and that one. So you need to transfer them here, yes? So one of them is this one. The other one is that whole package. And finally, I open a pair of curly brackets again. Then there are 2 more pairs that I haven't considered yet. So I will transfer them here. So this becomes curly brackets 1 and the next one. So it is very, very important to consider exactly the right number of curly brackets. If not, that's not correct. Okay, and then I go to 3-element subsets, but there is only one 3-element subset. You can either, to save time, you can just write A itself, or if you want to, you can write the whole set here. So I would prefer to write it in that way. Okay. One thing that I also mentioned about the power set, which I told is optional, so let me write it with a different color so you don't need about that. The power set of this set, if you want to learn, is a set containing all these subsets as elements. Yes? So here, so I open a curly bracket and I put them one by one here. So I will put this here so it becomes the empty set. And the next one, I separate it by a comma. The next one is this one. The next one is this one. So I just arrange them in a set. If I arrange them in a set, then that set is called the power set of the original set. I need to be careful about these curly brackets. If you see any mistake from my side, please just tell me. Oops. And then you close it. And of course, if you count 1, 2, 3, 4, 5, 6, 7, and 8 as predicted. Okay, but this one that I have written in this pink color is optional. It's good to learn it, but you don't need to learn it. Any questions? Okay, let me write another example for you and give you a little bit of time to think about this. Example. Specify the truth or falsity of the following statements. So number one, if A is a subset of B and B belongs to C, can I conclude that A belongs to C? So I will write them. I wanted you to think about these. If that is true, try to motivate why this is true. And if this is false, just try to provide a counterexample why this you think it is false. Okay? And so you can think about them. You don't need to write them with me. So number two. Okay, so I give you 2 or 3 minutes. Okay, so let us go to the solution to these problems. So I think most of them are false, if I just am right. So what is the first one? So the first one is false, yes? Could you come up with a simple example? By the way, if you want to give a counter example, it's better to make it as simple as possible, yes? You don't need to make it very elaborate. So just a very simple example is better. So for example, let me start with a very simple example of A. So if I write A, let me write it including only one element. And now I want to have a set B so that A is a subset, because I want to keep this right, but this is false. I want to make it in this way. If I can provide an example like that, then it means that I was able to refute this, yes? So A is equal to this one. I want to give an example of a set B, which contains A. Contains means that A is a subset of B. So let me write B as the subset of, in this form. So 1 and 2. Yes? And now this is right. By giving you these two examples, you confirm that this is true. A is a subset of B. But I want to write C in a way that B belongs to C. So if I want to give an example of a C, first of all, B should belong to C. So I would write just this one. Okay, and I think I can stop just here. I hope that you agree with me. If with these examples, if I say, what is this one? With these examples that I have provided, this is true because A is a subset of B. This is also true because B belongs to C. When you see inside C, you see B as an element, yes? This one is B, okay? Okay, so this is wrong, yes? I hope that you understand. This is false for these two examples, but B belongs to C is true, yes? Okay, so this B belongs to C. This is also true, but if I ask you what about A belongs to C, no, because for A belonging to C, I need to have something like this so that I can see A as an element. So this is false now. So this is a good counterexample. A simple, very simple counterexample shows that this implication is false because I respected these two. Both of them, in my case, are true, but the conclusion is false. So it means that this implication is not reliable. Again, let me repeat, it doesn't mean that you cannot cook up an example for which this is true, this is true, this is also true. But when I say that, is this a statement true or false? This means that for all possible cases. If this is for all possible cases true, then you would say this implication is true. Otherwise, even if you can find one single counterexample, it is enough to say that this implication is false. But implication being false doesn't necessarily mean that this is always false. It means that there exists at least one example that doesn't work. This is something that you need to know. Any questions here? So this is my counter example. Yes, I would call it counter example. Okay, let us, what is your opinion about number 2? Is it true or false?
It is false.
It is false, so yes. Could you come up with a simple counter example now?
No, I just imagined a.
Imagine doesn't work, actually. Imagine is good, but at the end you need to provide a counter example. Let us cook it up. Don't think it's, so I want to give the examples as simple as possible, and I want to write A and B in a way that A is not a subset of B. So I think that it is very good to start with A, two elements. Let me put it 1 and 2. and then B only, for example, one element, say 1. So far, I have respected this, yes? A is not a subset of B. Why? Because there is an element in A which is not in B. So this means that A is not a subset of B. So this is respected. But then I want to respect also that B is a subset of C, which is also true, but I want to make this false, yes? So we want to have an example C for which B is a subset. So definitely C should contain A, yes? So I can write it like this. Let me check if it works or not. Now let us try to understand it together. So in these sets that I have provided, do you think this is respected? A is not a subset of B is respected because there is an element on the left-hand side too, which is not in the right-hand side. So this is respected. What about B is a subset of C? Is it also respected? B contains only one single element, and that single element is an element of C as well. So this is also respected. But what about the last one? The last one tells you that A is not a subset of C. This means that you can find an element in A which is not in C. But can you find such an element? No. There are two elements in A. Both of them are in C. So is this a false statement or a true statement? You realize that this is a false statement. So again, I gave 3 sets. I respected the conditions that I have to, but the implication is not what is expected. So this is also a counterexample for the second one. These are not the only counterexamples, but at least I want you to understand, because even though these notions are very primitive and simple, but sometimes they are confusing. So I want you to practice about these symbols so that you can understand them better and better. Okay. So for example, the reason that I have brought this up, for example, do you remember we had this property of transitivity? If A is a subset of B and B is a subset of C, we showed that we can conclude always that A is a subset of C. Okay, that was something, this is a true implication, true statement. But I'm trying to say that, okay, if you want to conclude something except the ones that are in theorems, you need to be very careful. Might be they are not right. This is the purpose of this example, actually. Okay, now can I say that if A is not a subset of B, B is not a subset of C, it's definitely A is not a subset of C? Do you think, is it true or false?
It's false.
It's false. Okay, did you provide a counterexample?
For example, A could be, I don't know, 1 and 2, B could be 4 and 5, and C could be 1, 2, and 3.
Thank you very much. Yes, let us check. So A is this set, B is this set. So is this respected? Yes, because at least there is one element in A which is not in B. Of course, none of the elements. So that is true. Yes, thank you. This is correct, respected. What about this one? B is a subset of C is not true. Yes, that's also true. B is not a subset of C. And then A is not a subset of C is false, because A is indeed a subset of C. Whatever is inside A, it's also in C. So this is true again. Sorry, this is false. So this is also a counterexample. Okay, what about the next one? True or false?
I wrote true.
Number 4. What about others?
I think it's also true.
Okay. Anyone else? Because my impression is that this should be
I
false.
think it's false.
Yeah, I think it's false, but for example, I need to cook up an example for A so that it contains the element X. So I would say, for example, A is equal to, let us just take X itself. So the first statement is respected. X belongs to the set A. I don't want to have it as subset of B. So one element doesn't work, I think, yes.
I took
So
A to be X and 1
Yeah,
and
that
B
should
to
be
be
false.
X and 2.
So yes, let me write X and 1, you said, yes. And then what is B?
X and 2.
X and 2, exactly. Thank you. So let us see, so what is, let us see that are they respected or not. If A is this and B is this respected? Yes, because X is indeed an element of A. Is this also respected? Again, yes. Why A is not a subset of B? Because there is an element on the left-hand side, which is 1, and it is not inside the set B. So that is also respected. But is the last statement respected? No, because you see that X also belongs to B. So this statement is also false. So this is also a counter example of this. And finally, what is your opinion about the last statement?
I think this is the one that should be true.
Yeah, this one is true. So we want to show that if A is a subset of B, and of course this is clear, yes? Let me just draw a Venn diagram for you. Just, this is U, and the set A is contained in set B, yes? If something does not belong to B, it means that it should be somewhere here. When, of course, it is not in B and A is already inside, included in B, you immediately see that this point is not also in A. So that is actually a true statement, apparently, by this Venn diagram. Yes? Okay, but if this is true, we need to motivate that. So how should we motivate it? Okay, so I would use somehow proof by contradiction. So my goal is to show that X is not in A. Let us assume that this is not the case. My claim is that I want to show that under these conditions, this is inevitable. If you say no, so let us assume that this is not the case and X belongs to A. I want to show that X does not belong to A, but if you don't agree with me, then you have to agree that X belongs to A. Okay, now X belongs to A, and one of my assumptions is that A is a subset of B. So what is the immediate consequence based on definition of subset? I know an element is in A. I know A is a subset of B. What is the definition of being subset? It means that whatever is inside this set also belongs to this set. And on the other hand, you are telling me that X belongs to A. So based on definition of being a subset, I can immediately conclude that X belongs to B. But this is in contradiction with the second assumption, because in the second assumption, you are telling me that X does not belong to B. Okay, this contradicts the second assumption X does not belong to B. So therefore, X belongs to A is false, and X does not belong to A is true. Something along these lines. Okay, so that is a good practice to understand the difference between being subset, not being subset, belonging to, not being belonged to, or something like this. Okay, so there is a definition I want you to know about that, because we told that every set is a subset of a set. To differentiate all other subsets from the set itself, we talk about a proper subset. So a proper subset by definition is a subset of the set which is not equal to itself. As simple as that. So let me just write the definition here. We can have enough space here. So definition: if X, for example, is a subset of A and X is not equal to A, then X is called a proper subset of A. I just want you to know this word. Sometimes people talk about the proper subset. And usually, of course, this is not universally adopted, especially in the a little bit older books. You remember when I say, so I would write it simply like this: X is a subset, but I don't put this horizontal line. Usually when we say a subset, we put this. But now I will take it away and I just write X is a subset of A. Okay, this is not universally adopted, but especially in more modern books, we see have this one. This is comparable with this. So you can compare this one with this, with numbers. You can compare this with a strict inequality like this. But as I told you, that older books use this symbol for being a subset. Okay, and they also have these sets. Sometimes they write this and they put a negation on that one and then write A. So this means that X is a proper subset of A or whatever. Okay, but I think I will stick to this symbol. If I use this symbol, I mean that X is a subset of A and it is not equal to A. In other words, I would say that X is a proper subset of A. Okay, so let me also solve one example here. So when we talk about the proper subset, so if the cardinality of a set is n, what is the cardinality? What would be the number of proper subsets of this set?
Two n and then minus one.
Yes, 2 to the n minus 1. So if I ask you in this one, if I ask you write only the proper subsets, you will write all of them except the last one. That's as simple as that. That's just a word that I want you to know about. So let me write this example as well. The number of proper subsets of a set is 15 more than the number of subsets of a 4-element set. what is the cardinality of the set? Okay, so this is simple. Let me just do it. So then I would say I want to find the cardinality of my set. So I would say let n be the cardinality of the set. So n is missing. I want to find n. But when I read the question, the number of proper subsets, so what is the number of proper subsets? The number of proper subsets is equal to, as Alex said, 2 to the n minus 1. And I know that this number is 15 more than the number of subsets of a 4-element set. So the number of subsets of a 4-element subset of a 4-element set is equal to 2 to power 4. So this means that by reading this equation, I would see that this number is 15 more than this number. And then I need to solve this equation, which is very simple. 2 to power n minus 1 is equal. On the right-hand side, I will have 16 plus 15, which is 31. And I move this to the right, it becomes 32, but 32 is 2 to power 5. So this means that the cardinality is just simply 5. Yeah, very simple. I just want to understand about this concept. And then I will end this topic for subsets with one very important remark. But I want you to understand it yourself first. So remark. If I have two sets, let A and B be sets. Then, okay, if I tell you that A is a subset of B and simultaneously B is a subset of A, what do you think I can conclude from here?
B equals A?
Yes, they have to be equal. There is no other way. And of course, this is also the other way around. If two sets are equal, then each one of them is a subset of the other one. This is a very important remark, so later it will help us. If I want to show that two sets are equal mathematically, I need to prove two statements. I need to prove that the A is a subset of B. I also have to show that B is a subset of A. One of them is not enough. Then I could show that A is equal to B. So this means that this statement is equivalent to this statement. And this is always, if I want to prove some theorems in set theory for proving that two sets are equal, this is the only way that I do. I show that each one of them is a subset of the other one. To prove that this works, I take an element in the left-hand side and try to show that this element is also in the right-hand side. This is not finished. I have to take an element from this second one and show that that element also belongs to the first one. After these two steps are finalized and finished, then I am allowed to conclude that these two sets are equal. Any questions so far? So now this is a very important topic that we want to start now. That's the algebra of sets. So we want to do some operations between sets. Okay, so far we have some relations. This is not an operation between sets. This is a relation between two sets. I want to do some operations on sets. Okay, so I would write algebra of sets. So in the book it is, I think it's written operation on sets. So the first thing that I want to talk about is the complement of a set. If you want to compare it with the negative of a number, of course, they are completely different things, but even with numbers, I can talk about the negative of that number. I don't need to have two numbers, yes? If I want to add, I have to have two numbers. If I want to subtract, I have to have two numbers to subtract. But if I want to multiply a number by a negative sign, I just need one number. That's also more or less comparable to this situation. You can talk about the complement of a set, just one single set. So let me write this the title. So complement of a set. So let me write the definition. Let U be the universal set and let A be a set. The complement of A is denoted by, you write A and on top of that you put a small c. This is not power, this is just A, this is read A complement, okay? So you can read it A complement. It's denoted by this and it is defined as follows. So A complement is defined to be the elements which are in the universal set. Of course, you don't need to emphasize, but such that there is a property that X does not belong to the set itself. That is called the complement of a set. Yes. So if I want to ask about the complement of a set, I have to make sure that I have already given you the universal set. Because usually the universal set, we don't mention it explicitly, we assume that it exists somewhere and then we are working with sets. But if I want to talk about the complement set and I ask you to write down the elements of a complement set, of the complement of a set, you have to know the universal set explicitly. Usually when we are working with numbers in real analysis, so this set of real numbers is always implicitly taken as the universal set. But it is better to mention this explicitly. Okay, so let me draw a Venn diagram for you. So this is very clear what this is, yes? So I will take this one. So if this is my universal set, and then this is my set. So whatever is just outside this green one, what you see, which is not inside, if this is my set, whatever is outside this green part is the complement of A, yes? So let me write it here. So this one is called A complement. Okay, is that clear? Okay, so let me give you some simple examples. Let U be equal to x's belonging to n such that 1 is greater than x, less than or equal to 10. So whenever I use U, I mean the universal set. Let U be this and A be equal to 2, 7, and 9, and 10. Then, so what is the A complement? A complement means all the elements that are in the universal set, but they are not in the set itself. Okay, so what is the universal set? The universal set starts from 2 because it cannot include 1. 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is the universal set. I need to cross 2 away because 2 belongs to my set. I will take 7 away. I will take 9 away, and I will take 10 away. So what is left is 3, 4, 5, 6, and 8. So this is the complement of my set. Is that clear? Okay, so if I say, for example, let U be the set of all real numbers, yes? Then, okay, can you tell me, this is the set of rational numbers, and then I complement it. So what is this? How do you read this? Q complement means the numbers that are in the universal set. So it means that the numbers that are real, but they are not in the set of rational numbers. So it means all real numbers that are not rational. So what is that set?
The set of irrational numbers.
The set of irrational numbers. And that is denoted by this I. Okay, so let me emphasize, I is the set of all, is the set of irrational numbers. Irrationals, okay? So for example, if I tell you that, okay, the universal set is the set of integers, and then another set, I will call it the set of odd numbers. Okay, it's clear that the complement of this set would be the set of all even numbers. So the idea is very, very clear and simple. Okay, so this is also good to know. Let me write this as a remark, even though it's very clear. Yes, please.
I didn't understand.
Which one?
The universal real numbers and then a complement to it. Why rationals?
So this is the definition of irrational. If I do you know what is an irrational number? For example, the square root of 2 is an irrational number, yes?
Yes.
A number that cannot be, so when you say the set of rational numbers means the set of all fractions whose numerator and denominator are coming from the set of integers. They are integers and the denominator is not 0. Any number that can be written in this form is called a rational number. And if you put all of them with this property in a set, that set is called the set of rational numbers, yes? But if you know a little bit, square root of 2 cannot be written as a fraction. So this number is an irrational number, okay? And by the set of all numbers which are not rational is called irrational. So there is nothing that you don't understand because that's just the definition. If I ask you what is the meaning of being irrational, the answer is that a number is called irrational if it is not rational. So this is not something that you don't understand. This is just a name for the set of rational numbers and the set of irrational numbers. How you need to interpret this tells you that if a number is not in the set of rational numbers, I call it irrational, so it belongs to the set of irrational numbers. I don't know, could I help it or not?
Okay, and what about the real numbers? What
The
do we do?
real number is playing the role of this box, okay? The numbers are, in real numbers are, you can divide them in your head into two separate pieces. One piece is called the set of rational numbers. The other piece is called the set of irrational numbers. So I don't know what.
So yes. So it's the piece of real numbers that is not rational. So it's the irrational.
Yes, that's what I'm saying. That's the definition of
yes.
irrational. Yes.
Yes, okay, I understood. Thank you.
You're welcome. Okay, so what was the remark? Okay, so I would write it like this. Let A be a set. Okay, I tell you that X belongs to A. What you can conclude about this X with respect to A complement? If someone tells you that I see X is an element of A, I can immediately conclude that definitely that X does not belong to the complement. Is that clear? That's the meaning of being the complement of the set. Or, for example, you can have this situation. If someone tells me that X does not belong to my set, if I want to, I can conclude definitely it belongs to the complement. If someone tells that X belongs to the complement, if I want to, I can conclude that X does not belong to the set itself. And if someone tells me that X does not belong to the complement, of course, I can immediately conclude that therefore X belongs to A. So I think this is good to know, yes, even though they are very clear, but let me emphasize them by writing them explicitly. Any questions here? All of these implications are true. Okay, so now let me go and talk a little bit about the properties. So let me write a theorem. By the way, what I write as theorem are spread sometimes inside the problems in the book. So, but I want you to know them. If you want to study them systematically, it's better to remember these properties. But they are spread around the problems in the book sometimes. Okay. So let U be the universal set. And so let me write it like this. Then for every sets A and B, we have, okay, let me just do one by one. Number one, if I ask you, by the way, what is the complement of the universal set? What's the answer? What is the complement of the universal set? Is it hard? So it means that the complement of a set is defined to be all the elements inside U such that X does not belong to A. Now I am asking you, what is the complement of this? This means that the set of all X's in U such that X is not in U. So how do you interpret this? The set consisting of all elements of U that are not in U. What is this set?
It's an empty set.
It's the empty set, yes, exactly. So from the Venn diagram, that's also clear. So the complement of the universal set is the empty set. Another extreme, of course, you can immediately guess, yes? What is the complement of the empty set? What is that? Hopefully it's clear, but you hesitate to say yes. So that's the universal set. The complement of the universal set, nothing is left outside the universal set. An empty set is nothing. So when you talk about the complement of that, this is the whole set of the universal set. Okay, and then let me ask you another question. If I have one set, I complement it once, and then I get the result and I complement it once more. So what's the answer? The complement of the complement is what?
It's just A.
It's at A itself, thank you. Number 4 is interesting. If two sets are of this, having this relation, if I know that A is a subset of B, what do you think about B complement and A complement? Does they have relations together or not? In which, if they have, in which direction, what that relation is. So I know that a set is a subset of another set, this I know. Based on this assumption, I want to know what is the relation between the complements of these two sets. Do you have any? Yes,
The
yes.
complement of B is a subset of the complement of A.
Exactly, exactly. Thank you. So if you want to take complements from a subset relation, if you write it like this, then this becomes wrong. Okay, so what you need to do, you need to change the relation. You need to change the places of B and C. So you can write B complement is a subset of A complement. It's a very important property. And finally, number 5 is more or less trivial. If I tell you that two sets are equal, A and B are equal, what I can conclude about the complements, it's clear that if two sets are equal, the complements are also equal and the other way around. Yes, this is also the other way around, but that's the same story. Okay, so that's very important to know about these. Let me prove one of them. For example, number 4. So number 4. Before proving that, let us draw a Venn diagram to motivate ourselves that this is indeed the case. Okay, so if I draw a Venn diagram here, so I don't know how to do it here, but I need to respect that A is a subset of B. So for example, let me draw this to be my set B. Yes, this is B, and then let me draw another one inside that, which is A. So this is A. So here you see that I have respected that A is a subset of B. But when I say B complement means outside B. Outside B is here. Yeah, so I can just draw it with a different color. So this is outside B. So outside B is everywhere here. So I need to be careful not to go inside B. I'm not allowed to enter this green area. But this is outside. So what I have drawn, hatched here, this is a B complement. But if I ask you what is A complement, then A complement means outside A. So let me hatch them vertically. Outside A, so I need to hatch everything outside A. So these blue ones that I am drawing, I am allowed to go to the green area, but I'm not allowed to go to this gray area. I need to be careful about that. Yes? Now it is clear that everywhere that, so this one, this blue one is B, is A complement. Now, hopefully it is clear that wherever it is hatched with black, it is also hatched with blue, but not the other way around. So this means that this relation holds. B complement is a subset of A complement. It's not hard to understand. So, but this is a diagram, but this is not a mathematical proof. So I want to show that based on this assumption, I want to show that this is indeed the case. Okay, how should I prove this? If I want to show that this one is a subset of this one, there is only one way. I need to take a typical element here and show that this element is definitely on the right-hand side as well. Okay, so let us do that. So let me write it in details. So we assume, we know that A is a subset of B. We show that B complement is a subset of A complement. To show this, let X be an element in BC. We prove that X belongs to AC. You don't need to write it down, but this is the way that you need to think about. Or if you want, you can write it down as well. So is the idea clear? I have this assumption. My goal is to show this fact. So it means that I need to show any element on the left-hand side, in the left-hand side. So like X is also in the right-hand side. Okay. I know that X belongs to B complement. What can I conclude about from here? I can say that X does not belong to B. Okay, but can you tell me what happens when X is not equal to, when X does not belong to B and A is a subset of B? What can I conclude about X and A? A is a subset of B, but X is not in the bigger set.
X does not belong to A either.
Yeah, exactly. So X doesn't belong to A. But if X doesn't belong to A, if I ask you where is X, what is the answer? X belongs to the complement.
A complement.
Exactly, thank you. So that is as simple as that. So this is a very nice relation. Remember, if you have this subset relation, if you want to complement both sides, if you just do it like this is wrong. You need to be careful. When you complement it, you need to reverse the order, yes? So sorry, A is subset of B, you can conclude that BC is a subset of AC. And this is also very trivial. These are important facts about complements that you need to know. Any questions so far?
Babak,
Yes.
could you explain number 3 also?
Okay, so from the diagram, it is very clear. So if I ask you, if this is the set, when I ask you what is A complement, you should show me outside A, yes? So this hatched area is A complement. But now consider this hatched area. I ask you what is the complement of this hatched area. This would be this empty area, which is A. So this means that if I complement it once more, it becomes A itself. Or if you want, I can go to this example here. So do you remember, if this was A, this is the universal set, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I ask you find the complement of this, you cross the elements of A from the universal set and you got this. Now forget about the name. If I ask you what is the complement of this one again, you will definitely go back to your original one. Is that understandable?
Yeah, I understand.
So this means that if I take one complement, I go from here to here. If I take another complement, I am concentrating on complement of this. This is definitely, I will go back to the same original set. That is the
Yeah.
content of number 3. Yes?
Yes.
Okay, so let us see. What is going to be done now? Okay, now the real operation, let me at least start. I will not teach all of it, but just starting it. So this was a complement that I do on one set. Now I have 2 sets. I want to start defining the operations between 2 sets. Like, for example, addition between 2 numbers. We had an operation between 2 numbers. We had different operations between 2 numbers: addition, subtraction, multiplication, and division. Here in set theory, we have also the union, intersection, and subtraction. So these are the operations that we have in set theory. Okay, but let me go to the next topic here, the union of 2 sets. Okay. The union of sets. So definition. Let A and B be sets. The union, let me write this with this color. So the union of A with B is denoted by, so this is a little bit unfortunate. This union is also the U form, so you shouldn't get confused between the, whenever I want to write the universal set with hand, I will put this on top so that you understand that is the universal set. But if this is going to tell me this is the union operation, I will not put that. For typing, it's not hard to recognize between them, but when I want to write it with hand, it becomes harder. So whenever I mean union, I will always try to remember to put these 2 on top. The union of A with B is denoted by A this, and it is defined as follows. So we say that A union B is the set consisting of all those elements, again, of course, from the set of the universal set. Every element is coming from there, but with what property? The property is that X belongs to A or X belongs to B. So if you don't know, this symbol means or. Okay, and always this is a logical or. Okay. Logical or is always inclusive or. So inclusive means that it might happen that this is true, this is false, that is okay. It might happen that this is false, this is true, but again, that is okay. It might happen that both of them are true, that's also okay. So when I say that or, I don't mean that either this one or that one, but not both. Usually in everyday language, when we say or, we use it as exclusive or. We mean this one, not that one, or the other one, not this one. But in mathematics and logic, always the or is an inclusive or. So it might happen that this is true, this is false, we accept it. It might happen that this is false, this is true, that we accept it. It might happen that both of them are true, again, we accept it. So that's the meaning of the logical or. Okay, so for example, if I want to draw a Venn diagram for you, for example, let me draw something to represent this, these two sets. For example, the most general case might be this. I have this set. Oh, sorry. I have this set, and then I will have another set. Let me change the color here. For example, this one. And then, so let me, if you don't mind, let me, I don't know why this comes first. Let me see if it works in that way. Okay, now this is very strange because filling up is coming. In principle, filling should go away first, but the border goes away. Okay, forget about that. So here I have this set A, and then I will have another set B. When I say union, it means all these parts, yes? This is union. Okay, so what I mean, you see this part is only in A. That's acceptable because this is true, this is false. This part is also acceptable because this is true, this is false. But in between, it's also acceptable because now both of them are true. So when I say the union, I consider all of them. This is the union of these two sets. Yes? Is that understandable? Let me give you a numerical example that's easier. Example. So let A be equal to, for example, 2, 3 minus the square root of 2, and then I have B equals to 3 and 5 over 2, and for example, C is equal to 4 and 5 and 6, for example. Then, if I ask you what is A union B, what I need to do, I need to write all the elements of A and all the elements of B. I need to construct a set which includes all the elements that are either in A or in B or in both. But you need to be careful. You are not allowed to repeat an element. Okay, so I would prefer to do it like this. When I want to union two sets, I will start writing all the elements of one of them without thinking. And then I go to the next set and I start adding them here again. But if I have already added one element, I will not add it once more. So here I do not bring 3 here because this 3 is already there. So there is only one new element that I can bring there. So it is 5 over 2. So this is the union of A with B. For example, I can union A with C. Then again, I would immediately write the elements in the first set. And then when I want to append the elements of the second set, I need to be careful. If there is something repeated, I don't repeat it, okay? So, but there is nothing repeated here. So this is this one. I want you to understand this satisfies the condition, yes? If I ask you what are the elements here, you would say the elements here are either in A or in B. There is, of course, nothing in both here. If I ask you what are the elements here, you would say the elements are either in A or in B or in both here. For example, 3 is in both. That's also acceptable. For example, if I ask you what is C union B, then I would write the elements of C and then append the elements of B. So there is no repetition, so I don't need to be worried. And of course, you don't need to keep the order, but you need to be organized. There are difference between these two. So you need to be organized to make sure that you write everything down. But if you at the end write them in different order, but you have written everything correctly, that's also correct. So that's the notion of the union. Okay, so I want to stop here. Then next time I will continue teaching about the union. Okay, any questions so far? Okay, thank you. So I'll stop this.